Hello everyone, we are continuing the topic of diodes and we're going to start looking at the waveform shaping circuits using diodes. So the waveform shaping circuits that we're going to look at are rectifier circuits, clipper circuits, peak detector, and clamp circuits. These waveform shaping circuits are two-port networks and they're building blocks of the whole circuit. So in these for these two-port networks, we would like to find how Vout is related to Vi. In other words, we would like to find the transfer function of these circuits. In some circuits, the analysis is greatly simplified if RL goes to infinity or Iout is equal to 0. For this case, Vout versus Vi, or the transfer function, is called open loop transfer function. So the first waveform shaping circuit using diodes that we're going to look at is a rectifier circuit. So let's look at how Vout is related to Vi and find an expression that relates these two together. Knowing that the diode is a nonlinear element, we would expect to get a nonlinear expression for Vout versus Vi. So let's label the diode voltage and current. Current for this one is ID and this is VD. So KCL at this node tells me that Iout is equal to ID, and KVL in this loop is going to tell me Vi equals to VD plus Vout, or in other words, Vout is equal to Vi minus VD. And using Ohm's law, I know that for this RL, ID is equal to Iout, and that's equal to Vout over RL. So let's look at the conditions of the diode being on and off and figure out how Vout and Vi are related for these two cases. So starting with the case of diode being off, if the diode is off, ID is equal to 0 and VD is less than VD naught. So Vout, which is equal to RL times ID, that's going to be equal to 0 because current is equal to 0, and I know that VD is less than VD naught. From there, I know VD is equal to Vi minus Vout, that's equal to Vi because Vout is equal to 0. From there, Vi is less than VD naught. So the case of diode being on is when VD is equal to VD naught and ID is greater than or equal to 0. Again, I know Vout is equal to Vi minus VD, so VD is a constant value equal to VD naught, and ID, which is equal to Vout over RL from this Ohm's law, I know that it must be greater than or equal to 0. From there, Vout, which is Vi minus VD, is going to be greater than or equal to 0, and from there I know that Vi is greater than or equal to 0. So I can draw the transfer function, a graph of Vout versus Vi, and I know that for Vi values less than VD naught, the diode is off and Vout is going to be equal to 0, and for Vi greater than VD naught in this region, the diode is on and Vout is going to be equal to Vi minus VD naught. Let's see how we can use this transfer function for drawing an output voltage waveform for a given input voltage waveform. So let's assume you have an input voltage waveform like the given value V versus this is volt and in the units of volts, and this is the graph of Vi. It's a triangular waveform, and I would like to look at this transfer function that I calculated and draw the output voltage versus time. So the first step is to find the time intervals for which Vi is less than Vd naught, because I know that when the amplitude of Vi is less than Vd naught, the diode is off and V out is going to be equal to 0. So let's say Vi is changing between 0 and the maximum value of Vi, the positive peak. I'm going to show it with uppercase V and subscript plus a plus sign, meaning that that's the amplitude of Vi in maximum peak amplitude of Vi at the positive side, and this is negative V peak with the negative at the negative side. So for example, for a symmetric waveform, I have V plus and V negative equals to, for example, 10 volts. So this is 10 volts and this is equal to negative 10 volts. So V plus shows the amplitude, peak amplitude at the positive side, and V minus shows the amplitude at the negative peak. So now I have this triangular waveform, and I would like to find the output waveform versus time. So I need to find out the times at which for which Vi is less than 0.7. For example, it's a silicon diode with Vd naught equal to 0.7 volts. So for all these time values at t equal to, for example, t, output is going to be equal to 0 for this time interval. So for V between 0 and Vd naught, the output is going to be equal to 0. And the same goes here. At this time point, the value of Vi reduces from Vd naught, so V out is going to be equal to 0. For all these time points, Vi is less than Vd naught, so for all these time points, Vi is less than Vd naught. As a result, V out is going to be equal to 0, and the same goes for this portion. So and we set the output equal to 0 from this transfer function graph. We know that at these time intervals, V out is equal to 0. We set it equal to 0, and when the amplitude of Vi is greater than Vd naught, I know that the output is equal to input voltage minus a constant value of Vd naught. So this is a linear relationship. That means the shape of waveform is going to be the same for the output. It's just that the amplitude is going to be reduced by 0.7 volts. So for these time intervals, the amplitude of output is equal to the amplitude of Vi minus a constant value. So that's going to be my V out for the time intervals during which the diode is on.